Well, pre-calc students, this day has finally come. The last notes of the year. The last time you have to learn something from me this year. It's monumental. I'm sure some of you are doing backflips right now. Some of you might be sad. I hope. Well, anyway, the point is, it's the last one. And I'm excited. So we're talking about the derivatives of exponential and logarithmic functions. I apologize in advance. It's going to be kind of a lengthy one. I had to make sure that we went out with a bang. Nice long video. And it's not the most interesting, but hey, we're going to do it. But I do have to forewarn you, kind of got in an altercation today at Publix. As you can see with this knuckle here. Last pack of toilet paper. Me and this person just, well, words weren't cutting it, if you know what I'm saying. I'm kidding. I hurt myself cooking today. So I'm just going to apologize. It's not the prettiest thing. Anyway. I hope it entertained you as much as it did me and my wife. Alrighty, so let's get right to it. She called me dumb. I hope you can hear her say that on the video. I have evidence now. Alright, so
not like they didn't know.
The derivative of every exponential, a being a constant, u being the quote-unquote argument. So here we're talking about, 2 to the x power, e to the 5x, that'll be over here, just things like that. So here a is a constant. So if you have to find the derivative of an exponential constant raised to any kind of power, where u here is representing a function, then you write the original exponential, you multiply by the ln of the base, and then you follow the chain rule, and you multiply by du dx over there. And this is going to be the same for every single exponential, as long as it is a constant raised to a power. So, speaking of, here is a constant raised to a power. E, the natural base e. E raised to any exponent. This exponent could be a function in terms of x. Let's follow the rules. You write the original exponential, you multiply by ln of the base, and then you follow the chain rule, and you multiply by the derivative of the exponent. But ln of e is 1. They cancel out. So as it turns out, the derivative of e to u, whatever u is legitimately e to the u times the derivative of the exponent. What that means is the derivative of e to the x is e to the x. It's its own derivative. And as far as I know, it's the only function that is its own derivative. It's really stinking cool. Alright, so a word problem. And it seems rather, poignant in these times that we are learning in. The spread of a flu, let's call it, COVID-19, in a certain, unfortunately it says school, luckily that's not the case. So the spread of a flu in a certain school is modeled by this logistic equation, 100 over 1 plus e to the 3 minus t. Part A says to estimate the initial number of students infected with the flu. Well, that would mean before any days have passed. So t here is representing the number of days that have passed. So for part A, you're legitimately just saying, what is the population when 0 days have passed? You plug in 0 for t. You get 100 over 1 plus e to the 3 minus 0, which is just e to the 3. You grab handy dandy calculator, and you realize that there's no such thing as partial people, hopefully, and you round to the nearest whole person, so we have 5 people. If you type that on a calculator, just saving you the trouble of grabbing the calculator. That's what you get, 5-ish. It rounds to 5. Part B wants to know how fast, a rate. How fast is the flu spreading after 3 days? Well, we see here that t is 3, but we're talking about how fast is it spreading. We're actually talking about its rate of change. That's right, its derivative. But this is kind of hideous, isn't it? Tell you what, let me rewrite this so that it's not so bad. There we go, and believe it or not, that does make it easier to find its derivative. So for part B, when we go to find the derivative here, we're just going to follow chain rules with power rule stuff. So first things first, P prime of t, you're going to bring this -1 down to the front. Don't touch the inside. Decrease the exponent by 1. And then chain rule says that you have to multiply by the derivative of the inside. So now let's look in the inside. Derivative of this is 0, but hey, look, an exponential. We just talked about that. The derivative of every exponential is write the exponential and then multiply by the derivative of the exponential's exponent. Derivative of -t is -1. And these two negative signs will cancel, and this object has a negative exponent. So it cleans up, quote unquote, cleans up. Negative signs have canceled, 100 is on top, e to the 3 minus t is on top. And on the bottom, we bring this thing down and its exponent is now positive. 1 plus e to the 3 minus t, all quantity squared. And we've been asked, how fast is the flu spreading after 3 days? That legitimately just means plug in 3 into this. So what is p prime of 3? So you have 100 e to the 3 minus 3. Well, that's just 0. Oh, life is good. And down here we have 1 plus e to the 0, quantity squared. Well, e to the 0 is just 1. So down here you have 1 plus 1 squared, which is 4. 100 over 4, which is 25. That means that the flu is spreading at a rate of 25 people per day at the 3rd day. And part C says, when will the flu spread at its maximum rate? Well, in the past, we have found maximums by finding a derivative and then looking for where the derivative equals 0 and using a sign diagram. That legitimately means we could find the derivative of this derivative and create a sign diagram at its critical values and figure out where the maximum occurs, meaning it'd be increasing on one side and decreasing on another. I don't know about you, but I really don't feel like finding the derivative of this. So I'm going to cheat, and I'm going to grab my calculator. And I already have it typed up. It's kind of hard to see, but it's all there. And for poos and giggles, I went ahead and typed in that 25 that we have right here, okay? Let's see what happens. Oh, if you're curious to know the window, I went from 0 to 10 on my x's because I'm hoping that after 10 days, we've pretty much seen the behavior of this thing. And I went from 0 to 30 on a whim, basically because it was bigger than 25. Let's see what happens. Graph. Okay, now remember, this is our derivative. This is showing the rate of change. So every y value is actually a rate of change. Oh, well, it's got a really pretty peak. I wonder where it happens. I wonder what its y value is, and son of a b, it's at 25. My wife just gave me really big eyeballs. She must not know that I talk to you guys like that. Well, anyway, you could do the whole second trace maximum thing, but you would find out that this happens right there at t equals 3. So yeah, I cheated a little bit. But hey, that's what they wanted you to do in the calculus book. So the max rate of 25 at t equals 3 days. Ta-da! All right, moving on. Let's apply the formulas. At what point of this graph does the tangent have a slope of 21? Well, the tangent requires the first derivative. So we have to figure out what y prime is. Okay. Y prime equals. Well, the derivative at this -3 is just going to be 0, so we're legitimately just talking about the derivative of 2 to the t. You write the original exponential, you multiply by the ln of the base, and then you multiply by the derivative of the exponent. Okay, so write the original, multiply by the ln of the base, and then the derivative of the exponent is 1. Well, look at this errant mark. We'll just erase that. Here we go. All right, there's our first derivative. We want to know where does it equal 21. So set it equal to 21. And we're trying to solve for t. ln of 2 is a number. So since it's being multiplied here, trying to isolate t, I can divide both sides by ln of 2. So 2 to the t is 21 over the ln of 2. Now at this point, I want this t out of the exponent position. I could use log base 2 on both sides, but holy cow, there's already an ln over here. So instead, what I'm going to do, just to stop my eyeballs from melting, is I'm going to take the ln, come on red pen, the ln of both sides. Because when I do that, it's going to allow me to use my log rules and bring that exponent down to the front. I now have t ln 2 equals the ln of 21 over the ln of 2. I know, it's wild, right? Nested ln's. And last but not least, if you would like to get t by itself, you just divide both sides by the ln of 2. Well, that would be nested logarithms with a fraction inside a fraction. So before I divide both sides by ln of 2, I'm going to use a log rule here, and I'm going to say that this is the ln of 21 minus the ln of 2. I forgot to write n and 2 over here. There we go. Now I can divide both sides by the ln of 2, and it will look prettier, at least. Of course, you gotta grab a calculator to get this number. This number is about, I don't know, let's go 3 decimals, 4.921. That's your t value. It says at what point. That means x comma y. Well, we have x, t, we have it. So we have to figure out what y is. Y is 2 raised to the 4.921 minus 3. Save the trouble. It's about 27.297. So the coordinate where this thing has a slope of 21 happens at 4.921, comma, this ugly number, 27.297. We did it! Yay! Now for the fun stuff. What makes it fun? Well, up here in these boxes, I gave you those formulas. For the rest of the notes, the boxes don't have the formulas. That's right. We're going to derive them. That's more interesting. Now you know why it's true. So I've given you the directions to use inverses and the derivative of e to the x to find the derivative of ln of x. Remember what we wrote on the front. The derivative of e to the x is e to the x. Okay, so y equals the ln of x. I can cancel this ln on both sides if I use exponential base e. Like that. So what it's going to give me is that x equals e to the y. And now I'm going to find the derivative using implicit differentiation. Good thing we've already learned that, right? Basically, I'm going to find the derivative on both sides. So on this side, the derivative of x is just 1. And on this side, the derivative of every exponential is, write the original exponential, multiply by the derivative of its exponent. So the derivative of y is dy dx. And we are trying to isolate dy dx because, we're trying to find a derivative. So we divide both sides by e to the y. dy dx equals 1 over e to the y. Oh my goodness, that looks so bad, doesn't it? If only we had a value or something simpler for e to the y, something like, oh, look at that. E to the y equals x. So the derivative of ln of x is 1 over x. Now, more specifically, the argument didn't have to just be x. It could have been any function in terms of x, which means the chain rule would come into play. So it's 1 over argument. That's not a 4, it's a u. Times the derivative of the argument, or du dx. Neato mosquito. A line with slope m, meaning we don't know the slope, passes through the origin. Okay, at least we know one of its points, 0, 0. And it's also tangent to this graph. Ooh, talking tangents, we know we're going to be talking about first derivatives. What is the value of m? Okay, just so you have a picture in your mind of what's going on. Picture not drawn to scale, of course. ln graph looks something like this. And then there's a tangent line that is going through this point, and let's just say it's right there, and it's doing this. We want to know, what is the slope of that red dotted line? Okay, well, how do we accomplish that? Well, first things first. You know that if it's tangent to the ln of x, it has the exact same slope as the ln of x. Okay. That means its slope, m, must be y prime, which is 1 over x. Okay, so we know the slope is 1 over x, but we want to know the actual value for it. And here's how we're going to pull that off. This coordinate right here is the origin. We know it's 0, 0. Now this coordinate, the only thing we know about it is that it happens to be on ln of x. That means we don't have a value right here, so we're going to make one up. We're going to say this value is a. That means the coordinates here are a, comma, whatever the heck you get when you plug in a. If you plug in a, you get the ln of a. I now have two coordinates. Guess what? In Algebra 1, you learned a formula for finding the slope of a line given two coordinates. There it is. I'm going to use this as x2, y2, so I can have the ln of a minus 0 over a minus 0, giving me the ln of a over a. Oh, you know what? The derivative is also my slope. And if I want to know the derivative at a certain point, I have to plug in the x value. But the x value we're using at this point is a. So the slope according to the derivative is 1 over a. You see, what I have here is two different expressions for the slope of that line. But they're not allowed to be different. They must be the same. Which means that 1 over a must equal the ln of a over a. Well, since the bottoms of these two fractions are already equal, the only way this is true, so this means implies that, the tops must be equal. And we can figure out what m equals if we know what a equals, because if we know what a equals, we can put it right there. And that would tell us what m is. So we just solve for a. We need the ln to go away. So we just use e. Base e cancels ln. So what I know now is that a is the number e. What a strange thing to say, but e is a number. So a is equal to the number e. That means m, which was 1 over a, is actually 1 over e. And that is the slope of the line that is tangent. Oop, you can't see it. That is the slope of the line that is tangent to the ln of x and goes to the origin. And if you don't believe me, you're welcome to go to Desmos, type in ln of x, and in the next line, type in 1 over e, and then right next to it, put an x. And watch the magic happen. All right. Snatch. So now that we've talked about exponentials, you should have already been scratching your chin about logarithms, because, you know, you can't talk about one without talking about the other. And rather than me giving you the formula for the derivative of a logarithm, I thought it would be more interesting for us to see where it comes from. So I'm telling you, use change of base and the derivative of ln of x to find the derivative of log base a of x, where a is a constant. So y equals log base a of x. I'm going to use the change of base, and I'm specifically going to use base e so that I can use ln of x. So log base a of x will be written as the ln of x over the ln of a. Bet you never thought those log rules were going to be important again, did you? Well, guess what? The ln of a is a number. Since a is a constant, the ln of that constant is also a constant. So rather than me saying the ln of x divided by some number, I can say the ln of x times 1 over that number. I mean, it means the same thing. 5 over 2 is the same thing as 5 times 1/2. Now that I know that y equals 1 over ln of a, which, by the way, 1 over ln of a is just some constant, times the ln of x, I can now find the derivative of this. Okay, on the left, the derivative of y is dy dx. On the right, well, this is just a constant. And when you find derivatives, the constant on the front just comes along for the ride. And the derivative of ln of x we just found on the last page was 1 over x. So this is 1 over x ln a. And that's only if the argument was x. What if the argument was some function in terms of x? Let's call it u. Then the derivative of log base a of u, where u is some function in terms of x, would be 1 over u times the ln of the base again times du dx, because that is the chain rule. How fun! Deriving derivatives rather than me telling you the equation. So much more fun. Speaking of fun, ta-da! Look at that, chain rule fun. I made this question up because I'm mean or something. I'm not sure. I just thought it would be fun to do it. So what I have here is log base 2 of sine of 3x. This way we get to practice derivatives of logs and trig and the chain rule. This is, I'm going to rewrite it, log base 2 of sine of 3x. If you need to, you can always underline it in different colors, showing you all the things that you have to keep track of. So let's find the derivative. dy dx equals, first things first, the derivative of a logarithm is, scoop that down so you can see it, 1 over the argument unchanged. Well, the argument of this logarithm is sine of 3x times the ln of the base was 2, times the derivative of the argument. I'm actually going to write that, derivative of the argument. Derivative of the green thing. The green thing is the argument. We go, okay, well, nothing going on but the rent right here, so sine 3x times the ln of 2. All right, the derivative of any sine function is this multiplication dot. Cosine, don't touch the argument. And now you have to find the derivative of the argument, which is still the chain rule, which is the red derivative, which would just be 3. All right, a chain rule inside a chain rule. That gives me 3 cos 3x over sine 3x times the ln of 2. And guess what? We have a way of simplifying cosine over sine. Hooray, trig! It's cotangent, because tangent is sine over cosine. So I have 3 cotangent of 3x all over the ln of 2. Cool! If you're a nerd like me. All right, flip them over. The last side. Whew. It's all come down to this, guys. The last 2 questions of pre-calculus notes for the year. It says, this is f of x, find the derivative. And then we're going to find the domain of the derivative. Okay, this is pretty straightforward, right? F prime of x equals the derivative of every ln is 1 over the argument times the derivative of the argument. Okay, the derivative of the argument is just 1. Well, there it is. So what is the domain of this derivative? You're looking at that and you're going, simple dimple, Mr. M. The only thing that x is not allowed to be is 3. And I go, oh, how wrong you are. But why? Why is that not the domain of this derivative? Maybe it's because the original function had a restricted domain. You see, the domain of f of x is a problem for us. The derivative can't exist where the original function doesn't exist. The derivative of every logarithm, the domain of every logarithm is the same. The argument must be a positive number. That means the domain of f of x is from 3 to infinity, not including 3. So the derivative has to have the exact same domain. So the domain of f prime of x is also from 3 to infinity, not including 3. Pretty darn cool. So what's with all the extra space? I don't know, I was feeling generous. And, oh boy, where'd it go? I lost it. The last question. I saved the most fun for last. Fun. So I've told you that y is x to the x, and if you've never seen it graphed, go to Desmos. It does some pretty cool stuff. It's exponential, but it's redonkulously fast exponential. Go see it. X to the x. We have to find the derivative using a concept called logarithmic differentiation. And this is something I've never showed you before, but there are times when it comes in super helpful, especially when you're dealing with exponentials. And this is a special type of exponential. Logarithmic differentiation is exactly what it sounds like. We're going to use logarithms to help us find our derivative. So we start with writing y equals x to the x. Now, finding derivatives of ln's is easier than finding the derivative of a log, in my opinion. I mean, you just look at the formula. One is 1 over argument times derivative of argument. The other one is 1 over, and then in the bottom you've got argument times the ln of the base. I don't want to avoid all that crap. So what I'm going to do is I'm going to find the ln of both sides. Because what that's going to allow me to do is use my old logarithm trick that says when you have an exponent in the argument, you get to move it to the front. So the ln of y is actually equal to x times the ln of x. And we can now find the derivative with respect to x of both sides. So implicit differentiation. On the left, the derivative of every ln is 1 over argument times the derivative of the argument. But on the right, we have a product rule. I'm going to squeeze that up here because I've already written my equal sign. So I have that u is x and v is ln of x. U prime is 1 and v prime is 1 over x. And I have to fill out u prime v plus uv prime. That's going to go right here. U prime v, so u prime times v, which is 1 times the ln of x, plus u times v prime. But x over x equals 1. Oh, okay. Simple. And I'm trying to get dy dx by itself, right? It's so easy. I mean, we cancel all fractions the same way. You just multiply both sides by the reciprocal. The reciprocal of 1 over y is y, so we just multiply both sides by y. So dy dx equals y times the ln of x plus 1. And guess what? Just like before, we have an expression for y. Y is x to the x. Boom. Mic drop. And that's it, guys. I hope you enjoyed this year as much as I have. I know we're not officially done yet, but I have nothing more to teach you this year, other than life lessons if you'd like to learn a few, just because. I mean, who doesn't? I could pop onto Zoom and tell you some things, but I have taught you all the math I'm going to teach you this year. So head on over to my math lab and do the last assignment of the year for me. If you owe me anything or want to raise any of those old grades, go ahead and do it. You've got the next 2 weeks to do nothing for me except for make sure your grade is epic. Should you need anything from me, hit me up and remind, and we can always Zoom. And hopefully I see you all before summer break on a Zoom, maybe. Maybe I'll put together something the last week of school. If not, you better come say hi to me next year in the hallways. I'll be mad. I will track you down. Bye, guys.